Okay, good morning. So there is one very small part of this chapter left, of this section actually, so that is called Pascal's Identity. But if you don't mind, before that, let me just remind you about the binomial theorem so that this is somehow related. So if you remember, we talked about the binomial theorem that if I have two real numbers, x and y, and I have a natural number n starting from 1, 2, 3, etc., then we got a formula for expanding this. So we learned that this becomes a sigma, n choose k, and then I have the first number, x, to the power of n minus k. N is this n, and k is this k. That is the counter of my sigma, and it goes from 0 to n. And the next number, y to the power of k, yes? So that is called the binomial theorem. It helps us to expand a binomial to any natural power, not just 2 or 3. So we can just raise it to any power that we want to. So one thing that I want to mention, for example, if I want to calculate x plus y to the power of 7, what I have to write, I can write it as a sigma. K goes from 0 to 7, n is 7 in this problem. 7 choose k, and then I have x to the power of 7 minus k, y to the power of k. Okay? So then of course I can expand this sigma. Instead of k I put 0, so I get k x to the power of 7 minus 0, which is 7, y to power 0, which is 1. The next term becomes 7, 1, but then x to the power of 6y, and the next one becomes 7, 2, x to the power of 5y squared. The next one, 7, 3, x to the power of, let me be patient and write all of them. So this becomes 4y3, and then plus 7, 4, x to the power of 3, y to the 4, and then plus 7, 5, x to the power of 2, y to the power of 5, 7, 6, x to the power of 1, y to the power of 6, and then finally 7, 7, x to the power of 0, which I don't write, y to the power of 7. So first of all, you see that if I ask you how many terms are involved, there are 8 terms involved, yes, because if k had were starting from 1 to 7 is 7 terms, but it starts from 0, so you always have 1 term more than this power that you have here, yes? So if you count them, 1, 2, 3, 4, 5, 6, 7, 8 of them are there. Another thing is that you really don't need to calculate all of these coefficients, yes? So I hope that you remember, these are good to remember. N0, what is the answer to N0? It is 1, yes? It's always 1. And what is N1? N choose 1. It is the number of ways that I can choose one person out of N people. So that becomes how much? Okay. But from there, you have to start calculating things. But the good point is that if I do not have coefficients here, these coefficients are symmetric because of this rule that we know before already, yes? NR, n choose r, is always equal to n choose n minus r. In other words, if I have n alpha is equal to n beta, of course you can prove that this is if and only if. Alpha plus beta is equal to n. Yes? If you see the sum of these two numbers is equal to this number on top, then n choose alpha is definitely equal to n choose beta. And it can be shown that if this is the case, alpha plus beta should be n. Of course you should say or alpha is equal to beta. This is the trivial case. So what I mean is that, for example, if you calculate this coefficient, you really don't need to calculate this coefficient because they are the same. Yes, 7 choose 2 and 7 choose 5 are exactly the same numbers. Why? Because if I add 5 to 2, it becomes 7, and 7 is the number on top. But anyway, if the number increases, the number of coefficients that you have to calculate also increases. In this case, I know this is 1. I know this is 7. I calculate this one. By calculating this one, I also know this. By calculating this one, I also know this. Yes? And by calculating this one, I know this. By calculating this one, I know this. So this is completely symmetric. But at least I have to do some calculations. And if you remember, of course, you can always use the general formula, as I told you. N choose R is n factorial divided by R factorial, the difference between these numbers factorial. But I told you that in practice, it would be easier if you use this a little bit longer formula. But it is up to you. You really don't need to bother. For example, here, if I want to calculate 7 choose 3, of course I can use this original formula, but I prefer to write 3 consecutive numbers starting from 7 going down. So 7, 6, 5, and then write this number factorial in the denominator. But 3 factorial is exactly 6, so then I get 35. So I can calculate these numbers faster. But of course, if you want to use the calculator, it doesn't matter if you think about calculating these things faster by your hand. Okay, but I want you to learn about something that I want to talk about. That's also good. So let us multiply this power by this coefficient and then divide it by k plus 1 to see what happens, yes? So what I'm asking you, let us see what happens if I take this power and multiply it by the coefficient. So this becomes n minus k, multiplied by n choose k, and then divide everything by k plus 1. By dividing, I can write 1 multiplying by 1 over k plus 1. So let us calculate this to see how it goes. So you will see why this is useful to calculate. So you see, I take this power multiplied by its coefficient, but then divided by k plus 1. Okay, so let us see how it goes. So 1 over k plus 1, I just copy and paste it here, n minus k the same. But I will write the formula for that. The formula is n factorial divided by k factorial, n minus k factorial, yes? But now something interesting happens. Yes, this k plus 1 from here will be multiplied by this k factorial. It gives me k plus 1 factorial, yes? This n factorial is, let me write this in the numerator. Yes? And instead of n minus k factorial, I write n minus k multiplied by the previous natural number, n minus k minus 1 factorial. Yes? And now what happens, this n minus k here and that n minus k are gone. So what I get n factorial in the numerator, and in the denominator I have k plus 1 here. Instead of writing it as n minus k minus 1, I write it as n and I factor a minus sign out. I write k plus 1 and then factorial. Okay? Now do you, so I made a mistake, yes? And there is a factorial sign missing here. Okay, can I write this more compactly now? N factorial divided by k plus 1 factorial times n minus k plus 1 factorial. Can I write it more compactly now? Yes?
N choose k plus 1.
N choose k plus 1, yes? So this becomes n choose k plus 1. According to the formula, n choose r is this. So when I say n choose k plus 1, it means that wherever I see r, I have to replace it with k plus 1. And hopefully you agree with me, this will generate this. Yes, is that understandable? Now what is happening, if this is the coefficient of which term? Can you tell me? You see, 0, 7 is the coefficient of the first term. 1, 7 is the coefficient of the second term. 2, 7 is the coefficient of the third term. So when I say n choose k, it's the coefficient of which term? Which term? The number of term, the term number is one more than the k value. Yes, the k value is 0, but which term is it? This is the first term. The k value is 1 here, but which term is it? This is the second term. Yes. So n choose k is the coefficient of what? Of what? K plus first term. Yes. Do you agree? So that's the coefficient of k plus first term. But what is this one? Can you tell me what is this one? This is exactly the same one. If I increase k one more, this will give me that one. So that is the coefficient of k plus second term. Yes? So that is very nice relation. It gives you a very fast way to calculate things. So whenever you want to find the coefficient of the next term, say k plus 2, what you need to do, go to the previous term, take the power of x, multiply it by that coefficient, and divide by the number of term of the previous one. That is very easier and faster way to do it. For example, if I want to do it, you don't need to learn that, but I think it's good to know about it. So if I want to do it, I immediately write 7, x to the power of 7. And for finding this coefficient, I multiply 7 by 1, which is 7, and I divided how many terms I have written so far? 1 term. So I divide by 1. So the coefficient is 7. And the answer would be x to the power of 6y. I have to subtract 1 unit from the power of x and add 1 to the power of y. So let us go to the next one. I take this power, multiply it by 7, it's 42. How many terms I have written so far? 2 terms. 42 divided by 2 is 21. X to the power of 5, y to the power of 2. It's faster, yes? And if you go here, 5 times 21, how many terms I have written so far? 3 terms. So this is 7, so it is 35. So it is a very faster way to calculate things, of course, if that's important. And then, what is the next one? Can you tell me? What's the next one? Yes?
Same.
The same, yes, because you are supposed to multiply 4 by the coefficient and then divide how many terms you have written so far, 4. So you have to divide by 4. The 4 and 4 are cancelled, so what is left is 35. Yes? And then do I need to calculate anything? But of course, I told you, this only works if these coefficients are 1. If that's not the case, you need to put the whole expression here and then calculate it at the end. And I really don't need to calculate anything. How many terms are there in total? There are 8 terms. And I told you that this should be symmetric. So when I have 8 terms, 1, 2, 3, 4, I have 4 terms, and 4 more terms will come, but in symmetric way. So when this is 35, you see this was 35, the last one, that's also 35. So what is the next one? If you want, you can calculate, but you really don't need to calculate. It is 21, x2, y to the power of 5, and the next one would be definitely 7, x, y to the power of 6, and the last one would be y to the power of 7. But if you want, of course, you can calculate the same way. So you can say that I multiply 3 by, so I multiply 3 by 35. And how many terms you have written so far? 1, 2, 3, 4, 5. And you divide by 5. 35 over 5, 7 times 3 is 20. So you can continue in this way. I was thinking that's good to know if you want to do the things more efficiently and quicker. Is that understandable? But that is not something you have to learn. It is not given. Okay, now let us go to the last part of this lesson, and that is the Pascal identity, yes? Before doing that, let me calculate some of these for you. So for example, if a plus b to the power of 0 is actually 1, a plus b to the power of 1 is of course a plus b. If I have a plus b to the power of 2, this becomes a squared. It's very famous, even you don't need to use the binomial theorem. Of course, if you use it, you will get the same thing. And if you calculate this, a to the power of 3 plus 3a squared b plus 3ab squared plus b to the power of 3. Now, using this method, you can immediately calculate what happens for a plus b to the power of 4. This becomes a 4. Then I multiply 4 by this and then divide by 1, it becomes 4. Then it becomes to the power of 3b. I multiply 3 by 4, 12, divide by 2, 6. a squared, b squared. I multiply 2 by 6 is 12, divide by 3, 4. And of course the next one is also b4. Okay, now let us write these coefficients. So you see the coefficient here is only 1. The coefficients here are 1 and 1. So here you have 1 here and then you have 1 there. Coefficients here are 1, 2, and 1. The coefficients here are 1, 3, 3, and 1. The coefficients here are 1, 4, 6, 4, and then 1. Now I think you see the pattern, yes? Can you guess what are the coefficients for the next one? Of course, you already know how to calculate this one, but that's also another way. Can you tell me? Of course, I hope you agree with me that this will start with 1 and also will end with 1. But using this pattern, can you guess what will be the number here, the number here, the number here, and the number there? So because if I have 5, how many terms are involved? 6 terms, yes? So 1, 2, 3, 4, 5, 6. So what are these numbers? Can you see any pattern going on? Yes?
5, 10, 10.
Yeah, exactly. 5, 10, 10, and 5. Yes? So in order to get, so you see here, I add these two numbers, it becomes 2. I add these two numbers, it becomes 3. I add these two numbers, it becomes 3. And when it comes here, I add these two numbers, it becomes 4. I add these two numbers, it becomes 6. I add these two numbers, it becomes 4. So if I want to follow the same pattern, this is what I expect to get. And actually calculations confirm that. Yes, so you can confirm that this is exactly a to the power of 5, 5a to the power of 4b. 4 times 5 is 20, divided by 2 is 10, a to the power of 3b squared. And then again, a to the power of 2b3, and then you have 5b to the power of 4, and finally b to the power of 5. So this is not a coincidence, that is actually a representation of the Pascal identity. So if I want to write the Pascal identity, it is this. So if I give you n choose r, this can be written as n minus 1r plus n minus 1r minus 1. This is called the Pascal identity. Of course, for the Pascal identity to make sense, r should be at least 1. R cannot be 0. Yes? So r is less than, r should be somewhere between, of course, r should also be natural. This is called the Pascal identity. Okay, because whenever you are dealing with an identity, first you need to convince the audience that this is a true identity. And I want to prove it for you. The proof is simple. I want to prove it in 2 different ways. One algebraically, so you just use the formula, and one combinatorial argument. Okay, so algebraically is not probably that hard. So first of all, do you feel the connection between that Pascal identity and this pattern here? Let me just describe that one. Might be I was a little bit too fast. So here, this number, according to binomial theorem, is 3 choose 0, this is 3 choose 1, this is 3 choose 2, and this is 3 choose 3. And for example here, this is 4 choose 1, 4 choose 2, 4 choose 3, and of course 4 choose 0, and 4 choose 4. Yes? So this number that you see here, another name for this number is 4 choose 1. Another name for this number is 4 choose 2. Another name for this is 4 choose 3. Yes? Okay, but what was this one? This one was 3 choose 0 because it's on the third row. Yes? This is 3 1, and this is 3 2, and this is 3 3. So what we discovered is that any number that you like on the row lower low is the sum of these two. And that's exactly the Pascal identity, yes? Because 3 1 plus 3 2 is equal to 4 2 according to the Pascal identity if I choose n to be 4 and I choose r to be 2 in the Pascal identity, yes? If I replace n with 4, this becomes 4, this becomes 3, this becomes 3, 4, 3, 3. And if I choose r equals to 2, 2, 2, 1. 2, 2, 1. Yes? So that is just a representation of the Pascal identity. Is that clear, the connection between this triangle and the Pascal? So if I can prove that Pascal identity, I actually have proven this pattern working in general. Yes? Okay, for proving the Pascal identity, as I told you, I can do it in two different ways. Let us do algebraic. Let us do it algebraically first. Algebraically is probably simple, and I hope you agree with me. It's better to start from the right-hand side. So I would write the right-hand side is equal to, I just write the formulas. I write the formula for this number, so which is n minus 1 factorial in the numerator, this number factorial in the denominator, and the difference between these two numbers, n minus 1 minus r factorial in the denominator. And I will do the same thing here. So this becomes this number factorial in the numerator, this number factorial in the denominator, and the difference between these two. What is the difference between these two? That's exactly n minus r, because 1 and 1 will be cancelled, yes? Factorial. Yes, is that understandable? Yeah. Okay, so we need to take the common denominator because on the left-hand side we have only one expression involved. And what is the best choice for the common denominator here? The least common denominator, if I consider only these two, r factorial is enough because it is not only divisible by itself, it is also divisible by that one. And between these two, n minus r factorial will do the job, yes? And let us do this in our head. This divided by this one, what will happen? R factorial and all factorial are gone. N minus r, you can view it as n minus r times n minus r minus 1 factorial. N minus r minus 1 is exactly as n minus 1 minus r, so there is no difference. So this is the coefficient, extra coefficient, so that I have to multiply it in the numerator. Yes? And then plus, this is exactly that one, but r factorial divided by r minus 1 factorial. Hopefully you agree that becomes r times, yes? And I have to multiply r by its numerator. Okay, let me know, is that understandable or I'm going too fast? Is that understandable for you? Okay. Now what I am doing, this n minus 1 factorial appears here and there, so I can factor it out. N minus r is left, plus another r is left here, and n minus 1 factorial is pulled out. And then I have r factorial, n minus r factorial. But minus r and r are gone, so then I get n times n minus 1 factorial, which becomes n factorial, r factorial, n minus r factorial, and that's exactly equal to the right-hand side. Oh, sorry, the left-hand side. Yes? But that is not very fun doing this. Can you cook up actually combinatorial argument why this is true in the first place. Not based on algebraic calculations, based on counting strategies. So you need to set up a problem so that you can solve the problem in two different ways, equivalently, the same problem in two different ways. You know that the answers should match. Solving it in one way gives rise to this. Solving it in a different way gives rise to this, but because you are counting the same thing in two different ways, the numbers should match. That would be the idea of a combinatorial argument. Okay, I will start cleaning the board so that you can have a time to think about a problem, making a problem so that we solve that solves our problem here. Yes. Okay, do you have your problem? Think about n people that you want to choose R of them. Because at least on the left-hand side, you have the standard n choose R, and what's the meaning? The name is, its name actually crying out what to do, yes? You have n people, you want to choose R of them. How many ways you can do it? N choose R, yes? So this is my problem. I have n people, I want to choose R of them. Okay, but how can I understand this should be the same as the right-hand side then? So, let me see if this has been recorded. Okay. So, I have n people here, and an minus 1, the last one is an, for example. If I ask you in how many ways I can choose R of them, you know that, yes? It's n choose R. Yes? But how can I see the problem so that I can make it like the right-hand side? Look here. In both of them, n minus 1 is involved. So it means that this is somehow the number of ways that I can choose R people out of n minus 1 people. And this is the number of ways that I can choose R minus 1 people again out of n minus 1. And then I am claiming somehow if I add these two numbers together, it becomes the number of ways that I can choose R out of n. Okay, concentrate on this, yes? So let me just try to tell you somehow. Because you need to know, see that you are adding two things, so you have to somehow use the addition, the sum rule, yes? So it means that I should consider two different scenarios and count them separately and add the results, yes? So what I should do, I care about this. So assume that I start choosing R people out of these people. There are two possibilities for my choices. Either I have included this last person, for example, or I have excluded that person. Yes? Is that right? And I hope that you agree, if I count each category and I add them up, it should be the total number of ways that I can choose R out of n. Is that right? So you see, I am choosing R person out of these people. I am telling that in any choice that you see, in any choice that I have made here, either an is present or absent. If I count the number of the choices for which an is present, and I calculate the number of choices in which an is absent, and add them on together, I will get the same number. Yes, is that right or not? Can you feel it or not? Because in any choice that I make here, I want to choose R people out of this one. Okay, when the choice is done, I look into my group. Either an is present in that group or absent. There are no other choices, yes? There are no other alternatives. And if I count all the number of ways that I can choose R people in which an is absent, and I count the whole number of ways that I can choose R people so that an is present, and if I add them, it becomes the total number of ways, yes? Yeah, just nod your head. Is that understandable or not? Yes. Okay. So now can you tell me in how many ways, in how many of them, an is absent? In how many? Yes?
N minus 1, choose R.
R. Yes? Because if an is absent, it means I have one person less. So how many persons are there? N minus 1. But then I have to choose all R people from the left people, yes? So I have to choose R out of them. Is that understandable? So these are the number of ways that I can choose R people from these people with the condition that an is absent. Is that clear? Now let us see in how many of them an is present. If an is present, it means one of these R people that I am supposed to choose is an. So I have to choose R minus 1 person. Out of how many persons? Out of n minus 1 persons left. Is that right? So then it becomes R minus 1 and n minus 1 choose R minus 1. And then if I add them, hopefully you agree that this should be the same. So understanding these combinatorial arguments are very important. Yes or no? Let me just give you another challenge here. Okay, so I would write 0, 100, yes, plus 100 choose 1, 100 choose 2, 100 choose 3, and I continue this list to 100 choose 4. 100 choose 100. And I claim that this answer is 2 to the power of 100. Why is that? So I just want you to feel that combinatorial arguments are really powerful. If you want to do it algebraically, probably it is really, really hard because you have to calculate these 100 terms. The first few ones are simple. Of course, the last ones are repetitions from the first ones. Yes, because, so for example, 101 is equal to 199. Yes, but at least you need to calculate around 50 terms. Yes, and then add them up. And then, by the way, if you add them up numerically, then you need to convince yourself that that number is 2 to the power of 100. But 2 to the power of 100, of course, if you have computers, that's not hard. But if you want to do it manually, it's hard. So can you cook up a combinatorial argument? This is harder now. Can you cook up a combinatorial argument to convince yourself that this should be really the case? So when I ask you to do this, you need to think in this way. I need to make a problem and start counting it 2 different ways. One way, this is the answer. Another way, for the same problem, this is the answer. But because you are counting the same problem, the same number of items in 2 different ways, they should match. I can give you a hint. Think about sets and subsets. In set theory, 2 to power 100 is a famous number, yes? What is that? 2 to the power of n is what in set theory? Yes?
It's the number of subsets.
Of a set with n elements. So 2 to the power 100 is the total subsets of a set of 100 elements. Yes? So your problem is more or less clear now. So you can say that, let us consider this set. Let me write it with a sub 1, a sub 2, up to a sub 100. Consider this set with 100 elements. If I ask you how many subsets are there, the answer is simple. What's the answer? The number of all subsets. So let me call this set A. All subsets of A is equal to what? 2 to the power of 100, yes? That is clear. But can you say why, on the other hand, that number should also be this number? Yes?
Because when you do 100, choose 1, choose 0, there's that many ways to choose a set of zeros.
Yes.
And you continue that for each case.
Exactly. So this means that this is the number of ways, because when I want to make a subset, order doesn't matter. Yes, we know that for subsets, order doesn't matter. So it means that I have a choosing problem. So then this is the number of subsets with 0 elements. How many of them are there? 1, and that is the empty set. And that's correct. If you calculate this, that's also 1. Yes? And then what is the interpretation of 100 choose 1 in this problem? It is the number of subsets with exactly 1 element. Yes? And then how many of them are there? You don't need to calculate. How many of them are there? 100. And if you really calculate this, it becomes 100. And then, of course, it becomes harder to calculate these numbers. But I hope that you agree. If I ask you how many 2-element subsets are there, you will point to this number. And how many 3-element subsets are there, you will point to this number. So it is clear that if I start adding all 0-element subsets, all 1-element subsets, all 2-element subsets, continue until all 100-element subsets, it means that I have already counted all possible subsets. Yes? So that number is another way to count the total number of subsets. On the one hand, the total number of subsets is this one. On the other hand, the total number of subsets is this one. But the total number of subsets is a fixed number, so these two numbers should be equal. Yes or no? Understandable? Okay. Now, prove it algebraically. When I say algebraically, it means using formulas. I don't really mean do it 100 times calculating, taking common denominators. Yes. Find a way to prove this identity for me based on algebra. Yes? The reason I'm asking this because I want you to get experience about this one as well. I give you a hint. Use Binomial Theorem. Yeah, it seems a little bit unrelated, but it is not. So x plus y to the power of n, let me write the formula if you have forgotten. It is sigma n choose k, x to power n minus k, y to power k. K goes from 0 to n. That is the formula that you have. That's the formula, by the way, in algebra. One way to prove this was combinatorial one, but of course you can prove it using induction, or you can also use it in different ways, algebraically. But at the end, this is a formula not in combinatorics, it's a formula in algebra. Okay, how can I use this formula to be able to prove this is 2 to the power of 100? Yes?
If x plus, wait, if x plus y is equal to 1, no, wait.
No? But you are close.
I mean, if x up to the power of n minus k times y, k is 1,
Yes?
then we will get like each constant.
Okay, so this is the scratch work thing. What is the purified solution? Because this formula is an identity. I told you that this formula is valid if n is any natural number that you like, and if x and y any real numbers that you like. Yes? So any choice that you make for x and y from real numbers and any choice that you make for n from natural numbers will work for this identity. But then you need to be a little bit observant to see which choices will give this result to me. That's it. And that's very, very easy to guess now. Which choices of x and y and n will give rise to this equality? Yes?
N must be 100, and
Yes.
x and y must be 1.
1. Yes? So if I choose x and y equals to 1 here, so instead of x I put 1, instead of y I put 1, to the power of, instead of n I put 100. Yes? Then what will happen, this becomes sigma, k goes from 0 to 100, 100 choose k, instead of x I put 1 to the power of 100 minus k, multiplied by, instead of y I put 1 to the power of k. Yes? So you see that this, what I have written here is exactly this formula for these smart choices of x, y, and n. Okay, and then if I ask you, what can I write for this one? 1 plus 1 is 2. This becomes 2 to the power of 100. And then do I really need to care about these? No. Because 1 to any power is 1. 1 to any power is 1. If I multiply it, it becomes 1. So it's just 1. And then this becomes sigma. K goes from 0 to 100. 100 choose k. So that is exactly that formula. Do you agree? If I expand this sigma, it becomes the left-hand side. Is that clear? Yes or no? Okay, let me give you, because now you understand what is going on, I'm actually going a little bit far apart from Pascal, but these are also interesting things to know. So I will come back and give you some examples using Pascal Identity. And the lesson will be finished, okay? But before that, let me ask you if I have some examples here. So for example, can you calculate this number for me? So my question is this. Calculate 10 choose 0 minus 3 10 choose 1 plus 3 to power 2 10 choose 2 and then minus, you continue, plus 3 to the power of 10 multiplied by 10 choose 10. The problem asks you about the exact value of this sum. Of course, this is alternatively addition and subtraction. But I think you can see the pattern, yes? So if I continue this pattern until I reach here, what will be the final answer? The idea behind this is exactly the way that I used here. Okay, could you come up? It is clear that you have to have smart choices for x, y, and n so that the expansion of this becomes this. Anyone else? Yes?
So if you choose, for example, x equal minus 3,
X equals to minus 3.
And y equals to 1.
1. Let us see if it works. And n?
n is 10.
N is 10. Okay, let us see, is it correct or not? Instead of x, I put minus 3. Instead of y, you said I put 1. Instead of n, I put 10. And I start writing it out, yes? This becomes sigma. K goes from 0 to 10. 10 choose k. And then instead of x, you have minus 3 to the power of 10 minus k. And then y to the power of k.
Sorry,
Mm-hmm.
I think I messed up. I think you need to choose x and y. So x equals 1 and y equals minus 2.
Okay, so let us do that. X equals to
1 and y equals to minus 2.
y is equal to minus 3. In that case, I have to write this one to be 1 and this one to be minus 3. I have to also change these. Yes? Okay, let us see how it goes. The left-hand side, I don't have any problems to calculate. It's minus 2 to the power of 10, which becomes 2 to the power of 10 because 10 is even. But let me expand the sum and see that the sum is exactly this sum or not. If that's true, then I'm done. I put 0, but 10 choose 0 is 1. This is always 1, so don't worry about that. That's just 1. And then if I put 0, this becomes 10, 0. Minus 3 to power 0, which is 1. So far, so good. The first term, the first term. I go put k equals to 1. This becomes negative 3 to power 1. So it becomes negative 3 to power 1. 10 choose 1. And if I put k equals to 2, it becomes positive 3 to the power of 2 because 2 is even. Cancel that minus sign. And then it becomes 10 choose 2. Yes, it works. Yes, it is clear that if I continue, you need to convince yourself, of course, that if you continue up to the last one, it becomes 10 choose 10, and then 3 to the power of 10. Yes, that's correct. So the answer to this is 1024. So that was the pattern, yes? So I mean that you can play around with these. So as soon as you see that something like this is happening all the time, it's increasing. So you might think also about the binomial theorem. Might be there is a way that you can use the binomial theorem to answer that sum. And that's it. Just before leaving this, I want to mention that's a very famous combinatorial identity. So in general, this is true. Exactly with the same line of reasoning, I can prove that instead of 100, I can choose n, whatever n is. This is a very famous combinatorial identity. If n is a natural number, then that is always true. And that the proof is exactly like this, combinatorial way, or like this, by choosing x and y equals to 1, then you can get that. Yes? Is that clear? Okay, but if you, let me just go back, because we talked about the Pascal identity. Let me just remind you about, I wrote a Pascal identity to discover that this pattern is actually following. And then we proved it using combinatorial argument by choosing r people out of n in 2 different ways, and we also proved it algebraically. Now I want to give you some examples of the Pascal identity. Okay, so how can we solve these problems? Yes. So let me ask you this question. For example, let me write a multiple choice question here for you. So if I can find it here in my notes. Okay. So I give you this expression, 10 choose 4 plus 4 times no, 2 times 10 choose 4. Something is wrong. Yes, 10 choose 3. 10 choose 3 plus 2, 10 choose 4 plus 10 choose 5. I am asking you this one. I don't ask you the exact number. I ask you this one is equal to which one of these? 12 choose 5. 12 choose 6. 11 choose 6. 10 choose 6. That's my question, yes? So assume that this is option number 1, option number 2, option number 3, and option number 4. So I'm asking you, this question mark is equal to which one of them? And that is, I'm telling you, this is an exercise in Pascal Identity. And Pascal Identity here is in front of you. Okay, I want to wait a little bit for you so that you can solve the problem yourself. Okay, if you don't mind, let me write one more here, and then that lesson will be finished actually. So, I want you to simplify this expression as much as possible. I'm not asking you to calculate this. I'm asking you to simplify this coefficient, this sum, as much as possible. So I give you 5 minutes, then I will solve the problem, and then we are done for this chapter. Okay, could you come up with any answer for the first one? Is not actually hard. Yes?
12 choose
12 choose 5. I don't know, let me check. But what is the idea? The idea is, look, probably you understand that if I want to simplify something using the Pascal identity, I have to start from the right-hand side to the left-hand side, yes? Because on the right-hand side I have 2 terms involved, on the left-hand side I have only 1 term. So it is probably you need to think in that way. But then on the right-hand side, the number here and the number here are the same. And these 2 numbers differ exactly by 1. So you need to make the pattern right. So now, Dennis, do you want to say what you're supposed to do? So the question mark is equal to, what can I do with these 2 here?
I wrote 10 choose 4 plus
10 choose 4, thank you. So instead of this, I just copy and paste that. 10 choose 3. And then, instead of this one, I just repeat it 2 times. Then
the first 2 is equal to 11.
Yeah, that's a Pascal identity for the first pair, and another Pascal identity for the second pair, yes? So is that understandable for everyone? That's a Pascal identity, because these 2 numbers are exactly the same, and these 2 numbers differ by 1, so that is the right-hand side pattern. How should I go back to this left-hand side? Between these 2 numbers, I choose the bigger one, R, and between, so this number, whatever it is, this number is 1 unit more. So here, I combine these 2. Between these 2 numbers, I choose the highest one. And between, I take this number and add 1 to it. It becomes 11. And hopefully you agree with me, that's another Pascal identity. So between 4 and 5, that differ exactly by 1, I choose the highest one. But then I add 1 to this, it becomes 11. And then what?
It's another.
Okay, it's again another Pascal identity, yes? Because you see that they differ by 1, and that's exactly the same. So I choose the maximum value between these 2, so it is 5, and I add 1 to this, it becomes 12, 5. So I don't know what 12 choose 5 is, but I know that whatever 12 choose 5 is, and whatever this, they are equal. Yes? The next one is a little bit more tricky, but I can give you a hint again. The hint is that as far as you see, there is no Pascal identity involved, because for Pascal identity, these numbers that appear somewhere, they should differ by 1. the point is, there is no difference between this number and that number. Yes? Choose 2. It means that I have 2 people, I want to choose 2 of them, there is only one way. 3 choose 3 is the same thing. I have a group of 3, I want to choose all of them, so there's only one way. So there is no difference between choose 3, 3 choose 3, and 2 choose 2. But if I replace the first one with this one, then you will realize that Pascal identity appears, yes? So what I do, let me just write it here for you. So the sum that I am looking for, the question mark here, instead of the first term, you need to be a little bit observant to see that, okay, if I replace the first term with this one, then I will generate consecutive Pascal identities over and over again. So let me write the next one as well in front of you, and then we continue until the previous one is 98 choose 2, the last one is 99 choose 2, yes? Okay, but hopefully you agree with me, these two can be combined using the Pascal identity, and it becomes what? It becomes 4 choose 3. And now this one with the next one becomes another Pascal identity. So what is the answer? Because they differ exactly by 1, so I add 1 unit to this and I choose the maximum value. And then this one with the next one is another Pascal identity, so it becomes 6 choose 3. And if you continue, so you can continue this one, it becomes 99 choose 3. And then finally what will happen, it becomes 100 choose 3. Yes, so that is the answer that you have to provide here. Is that clear? So the only point for this problem was to change the first term to this one. Of course you can write 4 choose 4, but that is useless again. The only one that will work for this problem is to replace this with that one, yes? And this will give you a way to use the consecutive Pascal rules to combine them, so that the final answer will be this one. Yes? Any questions? Okay, so we are actually done with combinatorics and this chapter, and then probably we will continue with the next chapter, which is differential equations. It's completely like Math 4. So discrete mathematics, according to the syllabus we're supposed to do, is finished here. Okay? And what is left from Math 4 is not relevant. Don't worry. So what we have learned in Math 4 so far is enough for learning this part in Math 5. Okay, thank you.